So moving on with different trig identities, because there's a whole bunch of them. In the last lesson, we talked about reciprocal identities, as in cosine is 1 over secant, or secant is 1 over cos, and then the other two as well. We talked about quotient ones where tan is sine over cos, cotan is cos over sine, and then we talked about the main Pythagorean one where sine squared theta plus cos squared theta equals 1. And that allowed us to prove different identities. There is another set called the sum and difference identities, and it's these 6 that you will get. You don't have to memorize them. Okay. And what it boils down to is we can take the sine, cos, and tan of 2 angles, different angles added together by doing this. So if I had the sine of one angle plus another angle, it's the same as the sine of the first angle times the cosine of the second, plus the cosine of the first times the sine of the second. And then there's a similar identity for cos, although notice it is different. It's cos first, then minus sine. And then tan is quite different than the other two. And then we can also, we also have identities for if we take the sine, cos, and tan of some angles, subtracted another angle. So this is going to allow us to answer certain questions where we're asked to basically evaluate certain trig ratios, evaluate the trig ratios of certain angles, or evaluate trig ratios of themselves. That makes sense. Anyway, so here's some examples. So here you're given in A the cosine of pi over 12 times the cosine of 5 pi over 12 minus the sine of pi over 12 times the sine of 5 pi over 12. Well, if these were angles that we're familiar with on the unit circle, that would be pretty straightforward. We would just find them, take the cos of each one here, multiply them together, find those, multiply those together, and then subtract. But pi over 12 and 5 pi over 12 are not common angles on the unit circle, but we can make them one. If you look here, what trig identity is this the same as? If we take cos of one times cos of the other minus sine of one times sine of the other, it's the same as this one. Because we have cos minus sine. So I can rewrite this. I can compress it down to this. So this whole thing here is equal to the cos of the first angle, pi over 12, plus the second angle, pi over 12. So I've made it simpler to work with. Well, I can keep going. I can actually add these two to get what? 6 pi over 12. Well, 6 pi over 12 is the same as what? Pi over 2. If I reduce it. Well, that is an angle we're familiar with on the unit circle. So if we're asked to find the cos of pi over 2, remember cos is the x value, pi over 2 is up here. So what's the x value? 0. So at first glance, you're looking at this saying, well, how can I do this without using the calculator? Well, you can use one of the sum identities, the cosine sum identity. So that's actually what we're using, the cosum identity. To simplify it into an angle that we can take the cos of using the unit circle. This is a similar question where we've got this written out in expanded form. We have no idea how to do sine or cos of pi over 9 using the unit circle or 5 pi over 36. But we can simplify this using one of these. Which one does this represent? When we do sine cos plus cosine, which one is that the same as? Up here, isn't it? So I can rewrite this. Instead of using this long thing here, it's the same as the sine of the two angles in the question added together. And I can actually add these together. First of all, I have to make common denominators, which would be 36. So pi over 9 is the same as what over 36? 4 pi. So now I can add them to get 9 pi over 36. Still not an angle we're familiar with on the unit circle, but I can reduce it. What can I reduce it to? Pi over 4. Now I can use the unit circle to find that one. Well, sine pi over 4, that's the one that comes out in the middle here, and it's the second term. Root 2 over 2. So that was the sine sum identity we used. So if you get a long one like that and are asked to evaluate it, okay, compress it, simplify that fraction or simplify that angle as much as you can, and it should turn into a unit circle angle if you do it correctly. Another type of question you can see. What if we're asked to go backwards? And this is commonly where we use sine, cosine, and tan sum and difference identities. If you're asked to find the cosine of 7 pi over 12, well, that's not an angle we're familiar with on the unit circle. However, I could turn it into two angles I know on the unit circle, either added together or you can subtract it. Doesn't matter. Okay, so I'm not going to put that in just yet, because it could be plus, it could be minus. So how do we figure out what angles we can add or subtract that are the same as this? Well, over here, think of the angles we're familiar with on the unit circle. Give me one. Give me an angle on the unit circle that we often work with. A simple one. Pi over 6. What is that over 12? What is pi over 6 over 12? 2 pi. Give me another one. pi over 4. What's that? 3 pi over 12. Well, no, if I add those two together, it's not going to give me 7. So I need to go to another familiar one. Well, pi over 3. Can you see any of these two that you could add to get 7 pi over 12? Yeah, these two. So this splits up into 3 pi over 12 plus 4 pi over 12, which is the same as the cos of pi over 4 plus pi over 3. So I've split the angle up into two angles added together that I am familiar with. Well, how do we do this? We got to go back to our formulas. This is where we expand it. When we add, or when we take the cos of the sum of two angles, that's the one on the first column, second one down. Cos, and remember, those symbols are alpha plus beta, by the way, if you're not familiar with them. Okay. This is going to be the same as, because this is the cos sum identity I can use. This is the same as taking cos of the first one times cos of the second one minus sine of the first one times sine of the second. Those I know how to do. So notice, to do these kind of questions, you really need to be familiar with your unit circle. What's the cos of pi over 4? Root 2 over 2. So I can replace cos pi over 4 with that. Times the cos of pi over 3. What's the cos of pi over 3? Should know these. Minus the sine of pi over 4, which is also root 2 over 2. What's the sine of pi over 3? Root 3 over 2. Now that we've got values for all those, the trig of those angles, we can multiply this to get root 2 over 4. Minus, and remember, when we multiply two square roots together, it's the same as the square root of multiplying the numbers inside the square roots. Over 4. And you can leave your answer like that. If you want to put it into a single fraction, that's correct too. I would accept either one. You don't necessarily have to go to this step. Okay? So that would be our answer, or that would be our answer. Same idea with B. I need to split it up into two angles I know that are on the unit circle, and I've got a list, partial list here, by either adding or subtracting. Now remember, if none of these work, keep adding them. Like, what's another one? Pi over 2. That's 6 pi over 12. And then you can start going into the second quadrant. Okay? You could go 5 pi over 6. You can go 3 pi over, or sorry, 3 pi over 4, 2 pi over 3. But often this will be enough to figure it out. Can you see two angles here that I can add or subtract and it's equivalent to this? There's actually two choices. I could take these ones and subtract them, or I could take these ones and subtract them. Doesn't matter which one, it's going to give you the same answer. So let's do these two. So it would be 3 pi over 12 minus 2 pi over 12, which is the same thing as pi over 4 sine of pi over 4 minus pi over 6. Off here. So I'll go down here. Well, that's the sign difference one. You can see just by looking at this. So this is the sign difference identity. Which means I got to expand it out in order to find each of them and calculate the final value of sine pi over 12. And remember, you've got these formulas to work with. So you go to your formula sheet, go to sign difference, which is the one on the upper right. And that's going to be the same as the sine of the first angle, pi over 4, times the cosine of the second angle, pi over 6, minus the cos of the first angle, pi over 4, minus times the sine of the second angle, pi over 6. And now we go to our knowledge of the unit circle to actually find the sine and cos of all these angles, multiply those values together, subtract them to get the answer. Sine of pi over 4, 2 over 2. Cosine of pi over 6, 3 over 2. Minus cosine pi over 4, 2 over 2. Times the sine of pi over 6, 1/2. If you look at it, it's going to actually work out as the reverse of the previous one. You get root 6 over 4 minus root 2 over 4. So we can leave it at that, like I said, or if you want to put it into a single fraction like that, that is, of course, is also correct. Okay, the last one of these we'll look at is a tan one, and notice its degrees, which actually is easier because you don't have to do common denominators, equivalent fractions. So now you're thinking of your unit circle angles in degrees. Can you think of two common unit circle angles that you can add to get 75 or subtract to get 75? What are common unit circle angles in degrees? 45 degrees, 30 degrees, there you go. Okay, those two if we add 30 and 45 degrees. So that means this is the same as the tan of 30 degrees plus 45 degrees. If you wrote it the other way around, it's still going to be correct. If you wrote 45 plus 30, it's still fine. So this one's a tan sum identity. Which is a little bit more of a complicated formula. So we go back and it's on the lower left. It will equal the tan of the first one. It will equal the tan of the 30 degrees plus the tan of 45 degrees divided by 1 minus the tan of 30 degrees times the tan of 45 degrees. Now we're going to use our knowledge of the unit circle. So I'm just going to go off to the side here, tan 30. Well, that's, remember, that's y divided x. So at 30 degrees, that's the one here, where we've got root 3 over 2, comma 1/2. So that means it's going to be root 3 over 2, sorry, 1/2 divided by root 3 over 2. Same as 1/2 times 2 over root 3. The 2's on the top and bottom cancel each other out to 1. It's 1 over root 3. So that means I put 1 over root 3 and replace tan 30. Tan 45 degrees, a little bit more straightforward, because this one, they're the same, right? Root 2 over 2, comma root 2 over 2. So y divide x, anything divide itself, that's going to be 1. So now that I've got these, tan 30 is 1 over root 3, plus tan 45 is 1 over 1 minus tan 30, which is 1 over root 3, times tan 45, which is 1. And now I've got to simplify that. Okay. Well, first of all, simplifying the bottom, gives me that. I just multiply the 1 over root 3 by 1. But I've got to combine these by, and because they're fractions, I got to do lowest common denominators. What's the lowest common denominator of root 3 and 1? Root 3, which means that this stays as 1, but I have to multiply this by root 3. So I get that. Same common denominators on the bottom, root 3, except it's reversed this time. I got to multiply this by root 3 over root 3 to get the same denominator. This is already over the common denominator. And now I've got to change this to a multiplication question. 1 plus root 3 over root 3 times the reciprocal of this bottom fraction, root 3 over root 3 minus 1. Root 3's on the top and bottom cancel each other out to 1. left with that. So notice you do have to be familiar with your fraction skills, especially ones that involve tan sum and tan difference. Sine and cos sum and difference are much more straightforward. Okay. So that's another, this is probably the most common usage of sine and difference identities, is when we're trying to find the sine, cos, tan of angles that we're not familiar with on the unit circle, and we're trying to find the exact values, as in not using a calculator. Finally, one more type of question. We are given some information about two angles, two different angles. We are told that the sum of the first one, or sine of the first one, is 5/13, and that angle is in quadrant 2. That automatically tells me I should draw a coordinate grid and a triangle. That automatic, when I see this, I'm thinking, oh, I'm going to have to do a coordinate grid, triangle, Pythagoras. Okay. And then we have the cosine of the second angle is equal to 4/5. So I need to do two separate ones. So I've got a right triangle in quadrant 2. And remember how to draw it. The hypotenuse always comes up from the origin, from 0, 0. There's always one of the sides, it's always along the positive or negative x-axis, never the y. And then you connect the vertical side to make your right triangle. And this is alpha here, but we're using this as our reference triangle. Here it's in quadrant 4, so draw your hypotenuse first. Draw your horizontal along the x-axis. This time it's positive. Connect the third one to make a right triangle. This one's beta, but we use that as our reference triangle to find the actual trig ratios. Well, in order to find all the trig ratios, or the sum of them, or the difference of them, which we're eventually asked to do, okay, I need to know all the sides. In the question, it will always tell you two sides. So somehow you have to look in the question and figure out, okay, 5 and 13 are two sides. The question is, where do they go? Well, sine. Doesn't that mean opposite? Over hypotenuse. Which tells us that our hypotenuse must be 13. And our opposite, remember it's opposite to this angle coming out from the origin, is 5. So I have to find x. That's the x length. And I have to use Pythagoras. For b, well, I'm given the cosine, which is adjacent over hypotenuse. Hypotenuse here is 5. Adjacent is the horizontal side, 4. And it's the opposite that I don't know, that I have to figure out by Pythagoras. So I've got to do Pythagoras twice on two separate triangles. Once I have all the sides, I can do all the trig ratios or the sum of them. I can add them, I can subtract them, I can do whatever I want to them once I know all the sides. So this one, we've got x squared plus 5 squared is equal to 13 squared. And then we got to solve for x. So x squared plus 25 is equal to 169. Subtract 25 from both sides, and I get x squared equals 144. Remember, When we solve, this is a quadratic equation because it's got a square. When we solve, we have to do plus minus. So x is going to work out cleanly positive 12 or negative 12, but it can only be one of them. It has to be negative because we're in quadrant 2 if you look at the triangle. So x has to be negative 12. And now we do something similar to find the missing y length in the triangle that's involving angle beta. And it too is going to be negative because we're going down. So I'm going to add plus minus, but I'm going to choose the minus because I'm in quadrant 4. So here we would get 4 squared plus y squared is equal to 5 squared. 16 plus y squared is equal to 25. Y squared is equal to 9. Plus minus square root those. And you get y is equal to plus or minus 3. But because we're in quadrant 4 and the vertical side is going down, that means y is negative. Now I've got all the information I need. This is a lengthy question. So now we're ready to actually find these two. So the first one we're going to do is sine alpha plus beta. Well, this is the sine sum identity. So we got to write it out. We got to expand it. So going back to your formula sheet, sine sum is equal to the sine of the first one, alpha, times cosine of the second one, beta, plus cosine of the first one, alpha, times sine of the second one, beta. Now we go to our right triangle using alpha to figure out all of these, to get the numbers. So sine alpha, well, sine alpha, we're actually given it. So it's 5/13. Remember, it's not sine 5/13. Sine alpha gets completely replaced by 5/13. Cosine beta. Well, actually, I'm given that in the question. Cosine beta is 4/5. And we can see cosine beta is adjacent over hypotenuse 4/5. Plus cosine alpha. So I'm going to go back to my alpha triangle. Cosine will be adjacent, -12, over hypotenuse, 13. And sine beta, I got to go to the second triangle, the beta triangle. Sine is going to be the opposite, -3, over the hypotenuse, +5. So I'm here. And now I just simplify it. Multiply the fractions, add them together. So I get 20/65 plus, well, these two negatives multiplied make positive. So I get 36/65 which together make 56 over 65. The second one we're asked to do, we are asked to do seek alpha plus beta. Well, we don't have an identity for seek. But remember, when we found the seek of angles before, didn't we do the cos and then remember to flip? Same thing. Just do cos alpha plus beta. And remind yourself to flip. So cos alpha plus beta, going back, that's the cosine sum identity. So going to that, it's the cos of the first one, alpha, times the cos of the second one, beta, minus sine of the first one, alpha, times sine of the second one, beta. You don't need the parentheses here, not necessarily. And then remember, we're flipping this. So I'm just going to keep reminding myself. But I got to remember to flip this final answer when I get it. Well, we can actually use this stuff because we already figured them all out. Cosine alpha, we figured out over here. It was negative 12 over 13. Cosine beta, we figured out over here, and you were given it in the question, or you can figure it out from the triangle, 4 over 5. Minus sine alpha, which we were given, 5 over 13. Sine beta, which we had to figure out to be negative 3 over 5. And again, just going to remind myself. So I get negative 48 over 65. Well, I've got a minus. When I multiply these two, it's negative. So minus a negative means I'm going to add them. And I get 15 over 65. Which equals negative 3. Sorry, over 65, not 63. Equals negative 63 over 65. And remember, I got to flip. So my final answer is going to be negative 65 over 33. So it can look a little complicated at times. But it basically, when we use sine, sum, and sine, cos, and tan, sum and difference identities, it really comes down to these three types of questions, where you've got to use the formula sheet to help you. Okay? And then, of course, you have to know how to calculate with fractions, including square roots. The last one.